Hello, good day everyone. Welcome to Astronomy Session 4. In order to create an accurate map, a map maker needs a way to uniquely and simply identify the location of all the major features on the map, such as cities or natural landmarks. Similarly, astronomical map makers need a way to uniquely and simply identify the location of stars, galaxies, and other celestial objects. On Earth maps, we divide the surface of Earth into a grid, and each location on that grid can easily be found using its latitude and longitude coordinate. Astronomers have a similar system for objects on the sky. Learning about these can help us understand the apparent motion of objects in the sky from various places on Earth. This day, we will discuss about the Earth, Moon, and sky. Locating places on Earth. A great circle is any circle on the surface of a sphere whose center is at the center of the sphere. For example, Earth's equator is a great circle on Earth's surface, halfway between the north and south poles. We can also imagine a series of great circles that pass through both the north and south poles. Each of these circles is called meridian. They are each perpendicular to the equator, crossing it at the right angle. Any point on the surface of Earth will have a meridian passing through it. The meridian specifies the east and west location, or the longitude. By international agreement, longitude is defined as the number of degrees of arc along the equator between your meridian and the one passing through Greenwich, England, which has been designated as the prime meridian. The longitude of the prime meridian is defined as 0 degree. Positions in the sky are measured in a way that is very similar to the way we measure positions on the surface of Earth. Instead of latitude and longitude, however, astronomers use coordinates called declination and accession. To denote positions of objects in the sky, it is often convenient to make use of the fictitious celestial sphere. We saw in that the sky appears to rotate about points above the north and south poles of Earth. Points in the sky called the north celestial pole and the south celestial pole. Halfway between the celestial poles, and thus 90 degrees from each pole, is the celestial equator, a great circle on the celestial sphere that is in the same plane as Earth's equator. We can use these markers in the sky to set up a system of celestial coordinates. One of the fundamental facts of life at Earth's mid-latitudes, where most of these books' readers live, is that there are significant variations in the heat we receive from the sun during the course of the year. We thus divide the year into seasons, each with its different amount of sunlight. The difference between seasons gets more pronounced the farther north or south from the equator we travel, and the seasons in the southern hemisphere are the opposite of what we find on the northern half of Earth. With these observed facts in mind, let us ask, what causes the seasons? Many people have believed that the seasons were the result of the changing distance between Earth and the Sun. This sounds reasonable at first. It should be colder when Earth is farther from the Sun, but the facts don't bear out this hypothesis. Although Earth's orbit around the Sun is an ellipse, its distance from the Sun varies by only 3%. But that's not enough to cause significant variations in the Sun's heating. To make matters worse, for people in North America who hold this hypothesis, Earth is actually closest to the Sun in January, when the northern hemisphere is in the middle of winter. And if distance were the governing factor, why would the two hemispheres have opposite seasons? As we shall show, the seasons are actually caused by the 23.5-degree tilt of Earth's axis. This figure shows Earth's annual path around the Sun. With Earth's axis tilted by 23.5 degrees, note that our axis continues to point the same direction in the sky throughout the year. As Earth travels around the Sun in June, the northern hemisphere leans into the Sun and is more directly illuminated. In December, the situation is reversed. The southern hemisphere leans into the Sun, and the northern hemisphere leans away. In September and March, Earth leans sideways, neither into the Sun nor away from it. So the two hemispheres are equally favored with sunshine. How does the sun's favoring one hemisphere translate into making it warmer for us down on the surface of Earth? There are two effects we need to consider. First, when we lean into the sun, sunlight hits us at a more direct angle and is more effective at hitting Earth's surface. You can get a similar effect by shining a flashlight onto a wall. If you shine the flashlight straight on, you get an intense path of light on the wall. But if you hold the flashlight at an angle, if the wall leans out of the beam, then the spot of light is more spread out. Like the straight-on light, the sunlight in June is more direct and intense in the northern hemisphere, and hence more effective at hitting. In this figure, in summer, the sun appears high in the sky and its rays hit Earth more directly, spreading out less. In winter, the sun is low in the sky and its rays spread out over a much wider area, becoming less effective at hitting the ground. The second effect has to do with the length of time the sun spends above the horizon. Even if you have never thought about astronomy before, we're sure you have observed that the hours of daylight increase in summer and decrease in winter. So let's see why this happens. An equivalent way to look at our path around the sun each year is to pretend that the sun moves around Earth on a circle called the ecliptic. Because Earth's axis is tilted, the ecliptic is tilted by about 23.5 degrees relative to the celestial equator. As a result, where we see the sun in the sky changes as the year wears on. In June, the sun is north of the celestial equator and spends more time with those who live in the northern hemisphere. It rises high in the sky and is above the horizon in the United States for as long as 15 hours. Thus, the sun not only hits us with more direct rays, but it also has more time to do it each day. Notice in that the northern hemisphere's gain is the southern hemisphere's loss. There, the June sun is low in the sky, meaning fewer daylight hours. In Chile, for example, June is colder, darker time of year. In December, when the sun is south of the celestial equator, the situation is reversed. Let's look at what the sun's illumination on Earth looks like at some specific dates of the year when these effects are at their maximum. On or about June 21, for those who live in the northern hemisphere, called the summer solstice or sometimes the first day of summer, the sun shines down most directly upon the northern hemisphere. It appears about 23 degrees north of the equator, and thus, on that date, it passes through the zenith of places on Earth that are 23 degrees north latitude. The situation is shown in detail in this figure. Well, to a person at 23 degrees north, for example, near Hawaii, the sun is directly overhead at noon. This latitude, where the sun can appear at the zenith at noon on the first day of summer, is called the Tropic of Cancer. The sun's rays shine down all around the North Pole at the solstice. As Earth turns on its axis, the North Pole is continuously illuminated by the sun. All places within 23 degrees of the pole have sunshine for 24 hours. The sun is as far north on this date as it can get. Thus, 90 degrees to 23 degrees or 67 degrees north is the southernmost latitude where the sun can be seen for a full 24-hour period, sometimes called the land of the midnight sun. That circle of latitude is called the Arctic Circle. Now look at the South Pole. On June 21, all places within 23 degrees of the South Pole, that is, south of what we call the Antarctic Circle, do not see the sun at all for 24 hours. The situation is reversed 6 months later. About December 21, the date of the winter solstice, or the first day of winter, the northern hemisphere, as shown in the figure, now it is the Arctic Circle that has a 24-hour night, and the Antarctic Circle that has the midnight sun. At latitude 23 degrees south, called the Tropic of Capricorn, this one, the sun passes through the zenith at noon. Days are longer in the southern hemisphere and shorter in the north. In the United States and southern Europe, there may be only 9 or 10 hours of sunshine during the day. It is winter in the northern hemisphere and summer in the southern hemisphere. Now let us check your learning. Suppose the tilt of Earth's axis were 16 degrees. What then would be the difference in latitude between the Arctic Circle and the Tropic of Cancer? What would be the effect on the seasons compared with that produced by the actual tilt of 23 degrees? The Tropic of Cancer is at latitude equal to the Earth's tilt, so in this case it would be at 16 degrees north latitude. The Arctic Circle is at a latitude equal to 90 degrees minus the Earth's tilt, or 90 degrees minus 16 degrees. That is equals to 74 degrees. The difference between these two latitudes is 74 degrees minus 16 degrees is equals to 58 degrees. Since the tilt of Earth is less, there would be less variation in the tilt of Earth and less variation in the sun's paths throughout the year. So there would be milder seasonal changes. So how does a date change? The fact that time is always advancing as you move toward the east presents a problem. Suppose you travel eastward around the world. You pass into a new time zone. On the average, about every 15 degrees of longitude you travel, and each time you dutifully set your watch ahead an hour. By the time you have completed your trip, you have set your watch ahead a full 24 hours and thus gained a day over those who stayed at home. The solution to this dilemma is the international date line, set by international agreement to run approximately along the 180 degrees meridian of longitude. The date line runs down the middle of the Pacific Ocean although it jogs a bit in a few places to avoid cutting through groups of islands and through Alaska by convention. At the date line, the date of the calendar is changed by 1 day. Crossing the date line from west to east, thus advancing your time, you compensate by decreasing the date. Crossing from east to west, you increase the date by 1 day. To maintain our planet on a rational system of timekeeping, we simply must accept that the date will differ in different cities at the same time. A good example is the date when the Imperial Japanese Navy bombed Pearl Harbor in Hawaii, known in the United States as Sunday, December 7, 1941, but taught to Japanese students as Monday, December 8. What's today's date? Is one of the most common questions you can ask, usually when signing a document or worrying about whether you should have started studying for your next astronomy exam. Long before the era of digital watches, smartphones, and fitness bands that tell the date, people used calendars to help measure the passage of time. Even the earliest cultures were concerned with the keeping of time and the calendar. Some interesting examples include monuments left by Bronze Age people in northwestern Europe, especially the British Isles. The best preserved of the monuments is Stonehenge, about 13 kilometers from Salisbury in southwest England. It is a complex array of stones, niches, and holes arranged in concentric circles. Carbon dating and other studies show that Stonehenge was built during three periods ranging from about 2800 to 1500 BCE. Some of the stones are aligned with the directions of the sun and moon during their risings and settings at critical times of the year, such as the summer and winter solstice, and it is generally believed that at least one function of the monument was connected with the keeping of a calendar. Our Western calendar derives from a long history of timekeeping beginning with the Sumerians, dating back to at least the 2nd millennium BCE and continuing with the Egyptians and the Greeks around the 8th century BCE. These calendars led eventually to the Julian calendar, which was introduced by Julius Caesar, which approximated the year at 365.25 days, fairly close to the actual value of 365.2422. The Romans achieved this approximation by declaring years to have 365 days each, with the exception of every fourth year. The leap year was to have one extra day, bringing its length to 366 days, and thus making the average length of the year in the Julian calendar 365.25 days. The Gregorian calendar is the calendar we all use today. It was introduced in October 1582 by Pope Gregory XIII. It's a modification of the Julian calendar, reducing the average year from 365.25 days to 365.2425 days. So it shortened the calendar year by 0.0075 days in order to stop the drift of the calendar with respect to the equinoxes. To correct this drift caused by the Julian calendar, the date was advanced 10 days in October 1582. Therefore, Friday, October 1582 followed Thursday, 4 October 1582. Alright, so that's the end of our session. I hope you learned something. Thank you and have a great day. Bye!